And then what is neural networks? Like what I already indicated, neural network essentially is what people are trying to emulate human brain functions by combining or connecting multiple different simple neurons. And we consider perceptron as a reasonable model for one neuron. And then we are trying to stacking all those neurons together into a network, which is known as artificial neural network. One of the first artificial neural network models is known as multi-layer perceptron. So multi-layer perceptron is essentially a feed-forward stacking of perceptron models together. If you look at this illustration, so this is a multi-layer perceptron. So each blue circles here are representing a perceptron. And then if you look at the connection here, so essentially all the perceptrons are feed forward to another layer of the perceptrons. So by stacking all those things together, then you are hoping that this ensemble strategy is going to give you very good output prediction given the input. That's essentially the visual illustration of the multi-layer perceptron. So if you want to have a schematic illustration, then basically 1x and are essentially here actually the different measurements or features, and you give it different weights, and then you do the linear combination, and then you add an activation function for perceptron. It's a sine function. But more recently, people are investigating different nonlinear activation functions, including ReLU, ELU, tangent function, sigmoid function, etc., etc. So this activation function can have different functional forms. It depends on your problem. This is essentially one blue circle here. And then, like what I said, you do the feed forward, and then this artificial neural network model is known as a multi-layer perceptron. And a multi-layer perceptron for each layer, and in more recent deep learning terminology, people call it a fully connected layer, because from one of the neuron in one layer, it can go to any other neurons in the next layer. So that's why it's fully connected. But in old days, this is known as a multi-layer perceptron algorithm. So again, multi-layer perceptron is a feed-forward neural networks, and you can stack multiple layers together to hopefully derive better predictions. And then actually, what's the difference between old day multi-layer perceptual models and deep learning networks? If you have more than 3 layers of perceptrons or neurons, then typically people will call it a deep neural network models. If we write the multi-layer perceptual model in mathematics, then essentially you are going to do the feed-forward stacking. So this H is essentially the output of each layer. HL minus 1 is essentially the output of L minus 1 layer, which was used as the input feature, and it tried to do the linear combination or connection of those latent or hidden outputs or representations in the multi-layer perceptron, and then you go through a activation function to capture the potential nonlinearity to derive the next layer's output. So you just going through from the first layer with the input as the original input feature until you achieve the output label. So now for regression, you can directly use the output label. For the classification, then you can add a sigmoid function. If it's binary classification, sigmoid function is enough. If it's multi-label classification, you need to use a softmax function. Softmax function is essentially the extension of the sigmoid function for binary classification to classification for multiple label outputs. So this is a basic model construct or architecture for multi-layer perceptron. So here we notice that this connection or neural network weighting parameters at the Lth layer, it connects all the neurons in consecutive 2 layers. So it does not really capture so-called local dependency, as I mentioned earlier. So more recently, in deep network architectures, people are trying to capture the temporal spatial dependency relationships between both the input features as well as the hidden latent representations. And those are basically different types of deep neural network architectures. The famous ones are listed here, the convolution neural networks, recurrent neural networks, and the graph structured neural networks. And then with this model, then again, we need to formulate the optimization formulation and solve the optimization formulation to get the actual network model parameters W's. So this is another gradient descent or stochastic gradient descent training algorithm, depending on how you set up the training procedure. And the problem of deriving the gradient descent algorithm for the multi-layer perceptron is because actually it's a stacking architecture. So you are transforming the original features into multiple intermediate representations. If you compare this neural network architecture with, for example, linear or polynomial regression problem, in those problems, you only have one function. So either W transpose X equal map to Y, or W transpose phi of X map to Y. With the loss function, you can directly take the gradient with respect to the model parameters and then either try to find the closed form solution or try to solve it by gradient local search algorithms. But in a multi-layer perceptron, because you are going through this layer by layer, indeed, you need to take advantage of chain rules in calculus to update the network parameters. And this chain rule-based gradient descent is also known as backpropagation training procedure. Now, assuming that you have a general loss function, we already talked about multiple types of loss functions for classification based on different classifier types. And also we talked about regression using mean square error. So all of them can be the loss functions. So y hat is essentially the prediction. Y is going to be the observed output label. So depending on your loss function, you compute the loss of your prediction. And then based on that loss, you are trying to update those model parameters WL to derive or train the machine learning model, in this case, to train the neural network model parameters. So for gradient descent, again, you are basically trying to compute a gradient for the network parameters at each layer, but it is easy to compute, for example, the last layer, which directly give you the output. So if you only have one layer, you directly get the output, you will compute the arrow y hat minus y square. And then if you want to compute this neural network model parameters, then you can just take the derivative of the quadratic function, compute the gradient with respect to W, and then update W by gradient descent updating equation. But what about the second last layer? When you are trying to compute the second last layer, then essentially you need to do this backpropagation to propagate the gradient through the second last output. So this is a linear combination of the second last layer, and then this is going through the nonlinear activation of the second last layer. And when you are trying to compute a gradient with respect to WL, then you first compute the gradient with respect to ZL using this, and then you compute the gradient of ZL with respect to WL. So if you do the algebraic manipulation based on this chain rule, then you will end up with this. So this one is easy to compute because this one is based on G of ZL. For example, if we are talking about the second last layer, then G of ZL is essentially going to compare with the observed label. So you can just compute the gradient here easily. And then, of course, you need to compute the gradient with respect to this nonlinear activation function. That's how you compute this one. So you put this one here, then you will basically get the final updating backpropagation rule to compute the gradient to update the corresponding network model parameter at the nth layer. So essentially that's a derivation of the backpropagation. Of course, I'm doing it very quick introduction. And if you are interested in more careful or rigorous derivation of the training procedure for a multi-layer perceptron, you can go to some textbook talking about multi-layer perceptron or deep neural network training and try to go through the mathematics to understand how actually it was done in mathematics. We also have one example with simulated data points. This is a multi-label classification problem. And we simulated the data, and then using scikit-learn here, actually, we're going to construct a multi-layer perceptron. And this optimization algorithm is based on BFGS pseudo-Newton algorithm instead of gradient descent, but the backpropagation algorithm to compute the gradients and compute the approximate Hessian matrix is essentially the same procedure. And then you fit the data, and then you are trying to do the evaluation based on training and testing data sets accordingly. And the final part of this Jupyter Notebook is, again, we're trying to test the neural network models, AdaBoost algorithms on iris data sets. You can try to check the potential code segments to see how machine learning evaluation are typically done and how different machine learning algorithm perceptron, AdaBoost, and multilayer perceptron are performing on this specific data set.